Jnanam paramam dheyam. Knowledge is supreme.
So, let us consider a fluidized CSTR. Let us consider a fluidized CSTR and let us assume that a gas phase cracking reaction, where A goes to B plus C is occurring in this fluidized CSTR. Okay. And let us assume that the feed contains sulfur, which acts as a poison for the catalyst, and also assume that the cracking is a first order process. Cracking is a first order process, and if we assume that the decay, catalytic deactivation or decay of the catalyst is first order with respect to first order in activity, and its first order with respect to concentration of species A in the gas stream. Okay. So, now we can actually, so the schematic of fluidized CSTR, it looks like this, where you have a fixed volume for the CSTR, it is well mixed, and you have a feed which goes in. And let us assume that Ca naught is the concentration of the feed at the inlet, and V naught is the flow rate, volumetric flow rate of the feed at the inlet, and Ca is the concentration of the product stream, or concentration of species A in the product stream, and V is the volumetric flow rate with which the fluid stream leaves the fluidized CSTR. Now, a simple mole balance can be written for this system. So, the mole balance is, the rate at which species enters the molar rate at which the species enters the reactor, which is V naught into Ca naught. V naught has the units of volume per time, let us say meter cube per time, and the Ca naught, which is the concentration, is moles per unit volume, okay, minus whatever rate at which the molar rate at which the stream leaves the reactor, which is V, which is the volumetric flow rate with which the stream leaves the reactor, and Ca is the concentration at which it leaves the reactor, plus the rate of generation of the species A, that is equal to the rate of change of the number of moles of A with respect to time, which is the accumulation term. Now, for constant volume, which is true for a CSTR, for constant volume, the rate multiplied by rate in terms of the volume, that is moles per unit volume per time multiplied by the volume, should be equal to the rate defined in terms of the catalyst weight, that is the moles of A reactor per gram weight of the catalyst per unit time multiplied by the weight of the catalyst. So, these two have to be equal. So, incorporating this equality into the mole balance, we can rewrite the mole balance as V naught into Ca naught minus V into Ca plus Ra into V, and that is equal to dNA by dt. Now, dNA by dt can actually be written in terms of the concentration of the species, and so that will be V into dCA by dt. So, now the rate at which the reaction occurs, that is the rate of consumption of species A, is minus Ra equal to the corresponding specific reaction rate multiplied by the activity of the catalyst multiplied by the concentration of the species Ca. And the corresponding decay law is given by dA by dt, that is equal to the decay constant multiplied by the activity of the catalyst multiplied by the concentration of A in the gas phase. Now, if we know the rates of this reaction, that is the reaction rate, then next step we need to do in terms of designing the reactors, we need to use the stoichiometry and relate these terms here. So, using stoichiometry, we can find that the volumetric flow rate of the stream that leaves the reactor divided by the volumetric flow rate of the stream that enters the reactor should be equal to the molar flow rate Ft with which the species leaves divided by the ratio of the total molar flow rate of the outlet stream divided by the total molar flow rate of the inlet stream multiplied by the P naught by P, which is the total pressure at the inlet divided by the total pressure at the outlet multiplied by T naught. So, if at constant pressure, if P equal to P naught and at isothermal conditions T equal to T naught, so V by V naught simply reduces to Ft by F naught, Ft naught, which is nothing but 1 plus the net fractional change in the number of moles because of the reaction multiplied by X. So, now the conversion X is equal to 1 minus Fa by Fa naught. So, that is the conversion, and that is equal to 1 minus Ca into V divided by Ca naught into V naught. Now, remember that the reaction that we are looking at is A giving B plus C. So, therefore, the net fractional change in the number of moles is given by the overall mole fraction of A multiplied by this change in number of moles, which is equal to Ya into 1 plus 1 minus 1, that is equal to Ya naught, which is given by Ca naught by Ct naught, which is the Ca naught is the concentration of the species in the inlet stream, and Ct naught is the total concentration at the inlet stream. Okay. So, by using this expression, we can rewrite V by V naught as 1 plus epsilon minus epsilon into Ca into V divided by Ca naught into V naught, which is, and from here we can easily deduce that the volumetric flow rate of the stream that leaves the reactor should be equal to V naught into 1 plus Ya naught divided by 1 plus Ca by Ct naught. So, now, plugging in all these volumetric flow rate expressions in terms of concentrations etc. into the mole balance, we can rewrite the mole balance as after defining a residence time tau, which is the time that the fluid element spends inside the reactor, which is given by volume of the reactor divided by the inlet volumetric flow rate. And so, the mole balance will be dCA by dt, that is equal to Ca naught by tau minus 1 by tau into 1 plus Ya naught divided by 1 plus Ca by Ct naught plus K into A into tau into Ca. And the activity is given by activity A can be found from the decay rate expression for the catalyst, that is dA by dt equal to minus Kd into A into Ca. So, these two equations essentially characterize the simultaneous deactivation and the catalytic reaction which is happening in the reactor. And so, if one needs to obtain the dependence of concentration on time and the activity on time, then one needs to solve these two equations, solve the equation simultaneously, and one should be able to obtain the concentration profile as a function of time and the activity profile as a function of time. So, now we observe that the catalytic deactivation is a very serious problem, because it poses a strong major problem in terms of maintaining the conversion of the desired products, and as a result it has a strong effect on the economy of the company which is actually producing that particular product. So, therefore, it has a strong effect on the economics of that particular product, and as a result choice of reactor is extremely important, which will help in minimizing or avoiding the deactivation process. So, the choice of the reactor. So, what we are going to discuss now is to look at how can we use a particular choice of how can we decide what should be the choice of the reactor that will help in minimizing the deactivation of the catalyst, and with the objective of maintaining the conversion of the desired product. So we know that deactivation and reaction, they occur together. They occur simultaneously. So, therefore, the performance is severely affected. And as an offset, one could actually use different reactor configuration to maintain the conversion. So, what we are going to discuss now is to look at what are the different types of configurations that one has to use in order to minimize the deactivation of the catalyst, or rather in order to maintain the desired conversion. So, suppose if the decay is very slow, so naturally the choice of the reactor and the necessary steps that one has to take depends upon the speed with which the catalyst gets deactivated. So, if the decay is very slow, then what really works is basically using a temperature time trajectory, where the feed stream is constantly preheated and the temperature is increased slowly in order to minimize the deactivation and thereby maintain the conversion of the reaction which is happening inside the reactor. Suppose if the decay is moderate, it is a moderate decay, then it is suggested to use a moving bed reactor, and we are going to look at the design of this. The moving bed reactor can be used in order to minimize the deactivation, and then if it is a rapid decay, of the catalyst, then one needs to use a straight through transport reactors. This classification is based on the deactivation time scales as dictated by the corresponding decay constant. So, let us look at the slow decay, first case of slow decay. Suppose if the catalyst is decaying very slowly. So, if it is a slow decay system, then in order to maintain a constant conversion, the strategy is to increase the reaction rate by slowly increasing the temperature, feed temperature. So, this by slowly increasing the feed temperature, one could actually increase the reaction rate and thereby maintain the required conversion. And so, the classical setup which helps in such kind of a design is basically a fluidized bed. In fact, in many fixed bed reactors as well, such a strategy is employed. Suppose if this is a fluidized bed, it is a fluidized bed reactor, and then a preheater is added to the inlet stream. So, suppose the inlet stream is entering the preheater at certain initial temperature T naught, then as the reaction proceeds, the preheater constantly increases the temperature of the inlet stream so as to maintain a certain fixed conversion X. So, which means that the reaction rate at T equal to 0, that is at the start of the reactor, at the temperature T naught should be equal to the reaction rate at certain other time and certain other temperature T. And in terms of using the rate law that we have derived for catalyst deactivation, rate law for the reaction when the catalyst deactivation is simultaneously occurring. So, that will be A into T comma T. So, now the activity is a function of both time and temperature, and so minus R A into T equal to 0 comma T naught. So, these two quantities have to be equal in order to obtain the desired conversion. This quantity must be equal to this quantity in order to obtain the desired conversion, in order to maintain the desired conversion. So, now if we assume that it is a first order reaction, if we assume that it is a first order reaction, and also if we neglect the concentration variations, then we can write K of T naught into C A should be equal to the activity of the catalyst multiplied by the K, that is the specific reaction rate at a particular temperature, multiplied by the corresponding concentration C A. So, if we neglect the variations in the concentrations, then we can write that K T naught should be equal to A into K of T. But we know from the Arrhenius dependence of the specific reaction rate that we can rewrite this expression as K into T naught, that is equal to A into K T naught multiplied by exponential of E A, which is the activation energy for that reaction, divided by R into 1 by T naught minus 1 by T. So, cancelling these two, we can now find an expression that relates the local temperature, that is the temperature at which the reactor is being operated, with the activity and the temperature when the reaction was started. So, 1 by T should be equal to R by E A, which is the activation energy of that particular reaction, into ln A minus plus 1 by T naught. So, this is the relationship between the temperature at which the reactor has to be operated and the activity as a function of activity and the initial temperature T naught. So, now if we look at the decay law, which basically characterizes the deactivation of the catalyst. So, if you look at the decay law, so minus dA by dt is given by K d naught multiplied by exponential of E d by R, which is again the specific decay constant is also depends on temperature using the Arrhenius type expression, into 1 by T naught minus 1 by T multiplied by A to the power of n. But we know using the rate law we can relate the temperatures using the expression 1 by T minus 1 by T naught, that is equal to R by E A into ln A. So, by substituting this expression, we find that minus dA by dt, that is equal to the specific deactivation constant multiplied by exponential of minus Ed, which is the activation energy for the deactivation of the catalyst, divided by Ea into ln A into A to the power of n. So, this is equal to Kd 0 into A raised to the power of n minus Ed by Ea. So, this expression provides a way to find out what is the dynamics of the activity as a function of time. Now, if n is not equal to 1, that is the order of the decay or deactivation as a function of the activity is not equal to 1, then with assuming that the activity is 1 at time t equal to 0, the expression can be integrated and found that t equal to 1 minus exponential of Ea divided by Ea minus n into Ea plus Ed, that is the activation energy for the decay divided by R into 1 by T minus 1 by T naught, the whole divided by K d 0 into 1 minus N plus E d by E a. So, this expression provides a relationship as to how the temperature has to be changed as a function of time. So, this provides a relationship of how the temperature has to be increased in order to maintain a certain fixed conversion or desired conversion. Note that this relationship is valid only for independent deactivation. So, this kind of an expression provides an industry operating person as to how much the temperature has to be increased or how much preheating has to be done in order to maintain the conversion of the desired products. So, now if I look at if I plot this as a function of time and temperature, so this is the kind of profile that I will get. So, if the catalyst deactivation is very slow, then I can maintain the conversion by actually increasing the temperature of the gas that comes into the reactor, and the kind of profile and the kind of temperature rise as a function of time is captured in this graph here. So, suppose if it is a first order decay process, if the deactivation kinetics is directly proportional to the catalytic activity, and if the exponent is 1, then the relationship between the temperature and the time at which the temperature has to be changed is given by E a divided by K d naught into E d multiplied by 1 minus exponential of E d by R into 1 by T minus 1 by T naught. So, that is the expression one would get, and that sort of tells you what is the how the temperature has to be increased as a function of time when n equal to 1. That is basically the first order dependence on the deactivation kinetics on the activity of the catalyst. Now, as a next step, we look at what is the what kind of configuration that one has to use if the decay is moderate or a rapid deactivation of the catalyst. So, if you look at the moderate decay case, what is required here is, because the deactivation is fairly quick, fairly rapid, then there has to be a continuous regeneration or replacement of the catalyst inside the reactor in order to maintain a certain conversion, certain desired conversion of the products, a certain desired conversion, and therefore, it is important to have a continual regeneration or replacement of the catalyst. And there are two types of configurations, two reactor configurations have been used. So, one is the moving bed reactor, and the second one is the straight through transport reactor. These are the two types of reactors which is useful when there is a moderate or rapid decay of the catalyst which is used in the catalytic reaction. So, the moving bed reactor, the moving bed reactor is basically a reactor where the catalyst is constantly replenished, and the way the catalyst is replenished is, suppose if this is the reactor, it is a cylindrical tube reactor. Suppose this is the reactor, and the feed to the reactor is provided from the top, and the catalyst leaves the reactor and enters another chamber which is called a kiln, and this is used as a regenerator. It is used as a regenerator which regenerates the spent catalyst which is deactivated, and air is passed through this regenerator, and once the catalyst is regenerated, the regenerator catalyst is circulated back is circulated back, the regenerated catalyst is airlifted into another chamber which is called the separator chamber. So, it is a separator into the separator chamber, and once the catalyst goes into the separator chamber, it pumps the catalyst back into the reactor. So, this is how the replenishment, constant replenishment of the catalyst occurs in a moving bed reactor, and this helps in maintaining the conversion, and the products are removed from the bottom of the reactor. So, the pellets, the catalyst pellets that are typically used is about 1/8 inch or 1/4 inch. That is the typical size of the catalyst pellets that is used in these kinds of reactors. So, now let us try to write model equations in order to characterize the moving bed reactor and thereby maintain the conversion of the reactants into products. So, suppose if this is my reactor, and if the catalyst enters the reactor at a rate of US, that is the mass of catalyst per unit time, and if it leaves at the same rate, then one can write a molar balance and obtain an equation for the molar flow rate of the catalyst, molar flow rate of the species as a function of weight of the catalyst. So, this equation molar balance actually captures the dependence of the molar flow rate on the weight of the catalyst, and so this can be rewritten as F A naught into dx by dw equal to minus R A prime. Now, the rate of the reaction is now can be written as minus R A prime is equal to some activity of the catalyst A multiplied by the rate of the reaction at time t equal to 0. So, therefore, it can be written as A of t into the rate constant k multiplied by some function of the concentration C A, C B, etc. And the deactivation kinetics is given by dA by dt is equal to the deactivation rate constant multiplied by A to the power of n. So, let us assume that this is the decay model, this is the decay rate, that is the decay rate. This decay rate law is a simplified form, and in general the decay rate can depend on reaction / product concentration. And so, the contact time needs to be related with the weight of the catalyst in order to characterize this particular reactor. So, the contact time of the catalyst T is given by W by US, and from here we can estimate that at a differential time the amount of catalyst that enters the reactor is given by dW by US. So, from here we can now rewrite the mole balance in terms of the catalyst which enters the reactor and also the decay rate law accordingly, and the decay rate law is now given by dA by dt into dt by dW equal to kd divided by US into A to the power of n, okay, and that's nothing but dA by dW. So, that relates the decay of the catalyst as a function of the catalyst that is entering the reactor, and dx by dW is given by A by F A naught into minus R A prime at t equal to 0. So, one has to solve these two equations simultaneously. These two equations need to be solved simultaneously to obtain x versus the weight of the catalyst and A versus the weight of the catalyst. So, that characterizes the moving bed reactor. So, once we know this, we can use this in design parameters in order to appropriately design the catalyst. So, what we have seen in today's lecture is we have summarized the different types of deactivation of the catalyst, that is sintering, aging, fouling or coking process and poisoning of the catalyst. and we looked into the details of the mechanism of two types of poisoning. One is poisoning if the poison is present in the feed, or if the reactant or the product itself acts as a poison. And then we looked at fluidized CSTR to incorporate the decay law, which is based on the poisoning of the reactor, and then poisoning of the catalyst. And then we proceeded to look at what are the different reactor configurations have to be used depending upon, because it depends upon the nature of the deactivation. If the deactivation is slow, then one can use a temperature time trajectory reaction system, and if it's moderate or a fast reactor, one has to fast decay, then one has to use a moving bed reactor or a straight through transport reactor. Thank you.